Hi, my name is Kris Lokere. I'm an applications manager for signal chain products at Linear Technology. Let's talk about how to choose op-amps for precision multiplexed applications. If your system needs to measure many analog voltages, but not necessarily all at the same time, then a common approach is to multiplex these signals together into one output signal, so that you can then process and digitize each of these original voltage levels one at a time using shared circuitry. The obvious benefit is that this reduces the size and cost of the downstream components, because you do not need a complete measurement channel for each input signal. But doing this right requires some attention to detail, especially if you want to switch between channels quickly, measure accurately, and do all this at relatively low power consumption. This schematic shows what a multiplexed circuit could look like. You have several input signals, each buffered by an input op-amp. You have a multiplexer or mux. Muxes are available from a variety of component vendors and are essentially a collection of analog switches. The switches are controlled by logic signals that select which input connects to the common output. Notice that every time the multiplexer switches from one channel to another, the output signal changes value. So even if the input signals do not change quickly, the multiplexed signal does change quickly. So we can say that multiplexing signals increases the frequency contents of the combined signal. Therefore, any circuitry after the multiplexer must be able to respond to these transitions. If the output signal does not fully settle to the target accuracy, then the measured value of a given channel can depend on the value of the previous channel, which is the same as channel-to-channel crosstalk. Because the switches inside the mux have non-zero on resistance, it is often necessary to buffer the output using an op-amp. Now let's talk about how to choose which op-amp to use in this spot. Op-amps with low power consumption tend to be slow. In particular, op-amp slew rate is often very closely related to the op-amp supply current. That is because the internal current available to charge internal capacitors is a fixed proportion of the op-amp total supply current. The LT6020 is a new type of op-amp with a much higher slew rate than you would expect for the low supply current. In fact, the LT6020 has internal circuitry that automatically adjusts the slew rate based on the size of the input step. As a result, large input steps are processed just as fast as small input steps. The waveforms in these graphs show the impact on transient step response compared to a conventional op-amp of similar power consumption. For conventional op-amps, the large signal response is much slower than the small signal response. The LT6020, however, responds just as cleanly to a 10-volt step as to a ±200 millivolt step. This ability to slew fast and settle quickly to a new value, while still drawing only 100 microamp of supply current, makes the LT6020 a good choice op-amp to use as buffer after a multiplexer. Even if the op-amp after the multiplexer is fast enough, there is a separate issue which is not discussed as often. Most precision op-amps have internal protection diodes across the input stage to avoid reverse biasing the sensitive bipolar transistors at the input stage. When the multiplexer switches from one channel to the next, the input voltage at one terminal changes quickly, even when the output, and therefore the feedback node, doesn't change yet. This causes a large current spike to flow through the internal protection diodes. Where does that current come from? It must come from the circuitry connected to the input of the multiplexer. If that circuitry is high impedance or slow, then this current spike will cause a voltage glitch. The output of the system then attempts to follow that input voltage glitch, so that the output cannot settle accurately until after that voltage glitch has resolved itself. The LT6020 op-amp offers a unique solution to this problem. The input devices are very accurate, but also robust enough to allow more than 5-volt reverse bias. Therefore, rather than internal protection diodes, a pair of back-to-back Zehners protects the input. As a result, no current spikes occur for input steps of 5 volt or less. The waveforms in this graph show the effect of these op-amp current spikes on our multiplexed circuit. With a conventional op-amp after the mux, the input to the mux gets a significant voltage glitch, which persists as long as the output op-amp is slewing. With the LT6020 op-amp, not only does it slew faster, Also, the initial voltage glitch is much smaller. That is because no input protection diodes turn on. Let's see how the LT6020 op-amp performs in a multiplexer application in the lab. I have a board with 8 analog input channels, each buffered by a slow precision op-amp. These signals are combined in an analog mux, controlled by 3 logic signals. The mux output connects to the LT6020 op-amp buffer. To look at the behavior when the mux switches between 2 channels, I connect ground to analog input 1, and I connect a DC voltage source, for example 5 volt, to analog input 2. I then connect a signal generator to one of the control pins of the mux. By pulsing that control signal, the mux toggles back and forth between channels 1 and 2. The output of the LT6020 op-amp should then transition between the voltage of channel 1 and 2, so between ground and 5 volt. Let's take a look at the oscilloscope to see if things are working right. The yellow trace shows the mux control signal. The green trace shows the output of the LT6020 op-amp. And indeed, we see that each time the control signal to the mux changes, the op-amp output transitions very quickly and cleanly between the 2 analog voltage levels. This is thanks to the fast slew rate that I was talking about earlier. Finally, the purple trace shows the voltage at the input of the mux. Remember that I was talking about voltage glitches which can occur from input protection diodes turning on. This is the node where you would see those. You can in fact barely see a very small, very short glitch. This is due to the charge injection from the mux itself, which is a much smaller effect than input rush current through op-amp protection diodes. This glitch very quickly resolves itself so that the op-amp output can settle to the final value without problem. In conclusion, to work with multiplexed application circuits, you need an output amplifier with relatively fast slew rate, and you need to pay attention to whether it will cause voltage glitches due to input protection diodes turning on. The LT6020 has unique circuit features that make it work very well in these conditions. For more information about the LT6020, including its excellent DC accuracy specs, such as low offset voltage and low drift, please visit linear.com. Thank you for watching.